Started. All right, so welcome everybody to ML Scalability and Performance Reading Group. Today we're going to be covering this paper, Overlap Communication with Dependent Computation via Decomposition in Large Deep Learning Models. Kind of a mouthful. Essentially what it is an optimization that can be applied on top of tensor parallelism, specifically the variant of tensor parallelism that is applied with sequence parallelism as well. So before we dive in, let's just do a very brief recap of what it is they're actually trying to optimize. If I can open up the right tab here. Okay, so if we remember, in the original form of tensor parallelism from the Megatron paper, these tensor parallel regions are applied to multi-head self-attention as well as the feed-forward layers, right? And these, tensor parallel regions have an identity operator in front of them, followed by an all reduce. And then these are swapped in the backward pass. The identity becomes an all reduce, and the all reduce becomes an identity. So those are the collectives used in a traditional vanilla TP approach, are just all reduces. Funnily, you'll notice in this paper, if you scroll down a bit, they start talking a lot about all gathers and reduced scatters. So where are those coming from? Well, it's because subsequent to the original tensor parallelism paper, this other paper came out reducing activation recomputation large language models, also from NVIDIA, which applies a second form of parallelism to pair with tensor parallelism in transformer models and a sequence parallelism. Essentially, the authors made the observation that these operations between the tensor parallel regions, namely dropout, residual, layer norm, can be parallelized across the sequence dimension, aka they are independent on the sequence dimension. So for example, layer norm, we are normalizing the values along the feature dimension, not across the sequence dimension or across the batch dimension. So you can actually partition or shard these incoming output activations that are our input activations to the sequence parallel region, perform dropout residual layer norm in this parallel fashion, have reduced activation memory required on each device before ultimately needing to all gather before the next tensor parallel region. So just to kind of highlight the differences here and how this relates to our paper today, here instead of all reduces, we have all gathers and then reduced scatters. So namely, if we just specifically break down, say, the feed forward layer, starting right here on the right, the previous region is a sequence parallel region, meaning that on each device, it has some shard of the incoming input activation that's partitioned along the sequence dimension. So just like in our Megatron style TP, basically not Megatron style TP, but anyways, just like we talked about in our last session where I presented this paper on, basically, we need we're going to all gather the input activations, but the weights will be partitioned either row-wise or column-wise. The first one is actually this linear is partitioned column-wise. Second one is partitioned row-wise. And the idea being that we all gather our input activations, then we perform this sharded computation in this tensor parallel region, keeping the activations, the intermediate activations, sharded for as long as possible, until finally, here we need to actually reduce scatter the outputs in preparation for the sequence parallel regions coming up next, right? So we would reduce the output activations so that we have complete results on each device and scatter along the sequence dimension so that we can then parallelize the dropout residual layer norm across the sequence dimension and keep our peak activation memory required smaller. And yeah, so hopefully that makes sense. The idea here was just to reduce the amount of activation recomputation we need to do because we're already applying this memory optimization here and reducing peak memory required, so we don't have to use AC to rematerialize all those intermediate activations all the time, which is like burns extra compute. So that's the stage. That's what they're trying to optimize, is that this all gather and reduce scatter are basically fully exposed in the vanilla form here. If we're not talking about any fancy optimizations, these are nickel collectives, which are multi-device collectives, which will be fully blocking, and this linear in this tensor parallel region cannot begin on any device until this all gather is completed on all the devices, until all the data is available. We're moving a lot more data around. So what this paper is, if we look at the title again, it is trying to overlap that communication, like the all gather, for example, with the dependent computation, like the first linear, the matmul, via decomposition. Okay, so we'll see what that means in a second. But hopefully that sets the stage and everybody has the proper context to understand like what we're looking at, what we're trying to optimize. Okay, so moving into the intro, actually before I get started, I should just say and give everybody a warning, I actually found this paper not super helpful. It's okay. I found it a little too abstract. It's more like algorithmic focused. So we'll have a bonus resource after this. I'm just going to go over some key highlights of this and not go over the whole thing like usual, because I think there's actually a better resource in the paper to understand the technical details of how this actually works, because that's really where the interesting and important stuff is. So yeah, you'll see what I mean. So to get started, let's just briefly go over the intro. It says to create more overlapping opportunities, as we just discussed, the proposed technique decomposes the original computation and communication operations into finer grained ones and directly works on each data shard individually instead of waiting until all of the data shards are ready. The data can be either operands or computation results. A communication operation that transfers data across multiple devices, like all gather or reduce scatter, like we just talked about, is decomposed into a sequence of finer grained point-to-point collectives, which they call collective permutes. So this is very important. Instead of this huge all gather, it's decomposing it into point-to-point collectives. Very important. Based on the number of partitions specified by the model parallelism strategy. The consumer or producer operation, Einstein summation. So essentially they're just using einsums as like a generalized way to say either, basically a matmul is how we can think of it. It's a matmul in practice. Is then also decomposed into a sequence of finer grained ones, each of which performs only a part of the computation, with a simple accumulation or concatenation operation to combine the partial results. Okay, and then it basically just says this is semantically equivalent to the original form of this, and they also mentioned that they propose, in addition to this decomposition-based approach with the point-to-point communication, they also introduced like a new instruction scheduling algorithm that basically tries to schedule all these async send and receives and matmuls in such a way that it achieves as much overlap as possible. And then they also mentioned that this is, in the implementation side, it's a compiler-driven implementation, meaning that in the XLA compiler, it will do some pattern matching and automatically apply this optimization to regions where it sees these like all gather matmuls or matmul reduced scatters, right? So that would correspond to this, right, where we do all gather and then matmul, and we go through our tensor parallel region, then matmul, this last matmul, reduce scatter, right? So that's what it's looking for, and it's going to replace that region of the graph with like this micro-pipelined implementation. Cool, so that's the introduction. We can mostly skip past this. It's just like defining what these collectives are, which we know. Typical partitioning strategies for transformer-based models, we already know. So let's go to the overview and talk about the actual meat of the paper here. So this page is where it actually begins. So this first part talks about the all-gather matmul and how it decomposes that. The second one is the reduce scatter, matmul reduce scatter. So let's start by looking at this paragraph and comparing with this diagram below, which is what it corresponds to. So it says, Figure 4 uses an example to demonstrate how the proposed technique works for all gather cases. In this example, each device partition has one shard of the operand A. So in this example, we're doing an A matmul B equals C. Okay. So the left operand A is partitioned where device 0 has A0 and device 1 has A1. Okay. And in the current system, just vanilla, nickel collectives, we'll start an all gather. All gather collective, and it will run, and it will basically block. And when the entire A, so in this syntax, I show like A0, A1 with brackets to represent like an all gathered concatenated full A matrix of all the shards. Once that full A is available on both devices, then the corresponding matmuls can occur. This would be like where we're entering the tensor parallel region right here, this first linear. Okay. And you can see how that's blocking. There's no overlapping. Okay. These are like, just to clarify, we're looking at, these are like fake traces. If anybody's familiar with GPU traces, these are like kind of like fake ones. The proposed overlapping scheme, what is proposed in this paper, however, does not wait until the entire data is ready. It has a weird phrase in this paper, wait until the entire data to be ready. Anyways, it does not wait until all the data is ready before the computation. Each device starts from asynchronously sending the data shard that originally resides on it to the other device while computing the partial result using the available data shard at the same time. So, and this is by the time the first partial result is generated, the data shard required by the second half of the computation has been received. Therefore, the second computation can be continued immediately. And it says, so if we look at, and then, okay, it's just an extra dynamic update slice operation is needed for each partial result to update the corresponding slice in the final result, which is initialized with all zeros. So this is just saying we gave this weird abstract name for basically like a index assignment operation, just like we have an output buffer allocated, and we have like a partial result that we can assign to like index 0 at the end of the first operation, and the second one that'll be like index 1. So to correspond, let's look at the diagram now. So I'll zoom in a little bit. This is the overlapped implementation. You see each device starts by kicking off an async send 0, A0. It sends its local shard to the other device. This is just a TP degree of 2, the 2 devices. Partition 1 sends its local shard, A1, to partition 0, right? It kicks that off, and while that's happening, it will then compute the local portion of the output that it's able to calculate with the given local shard of data, which is A0 and B0, mapmul to get C00, right? And then it does dynamic slice update, quote unquote, which is just basically storing that result in this output buffer. Then async, and this is also the corresponding thing is happening on the other device, right? And you see it calculates C11 with A1 and B1, okay? Then async receive, it finishes basically what this is corresponding to. Again, this is very light on detail. It's just like putting the word async in front of stuff and like not actually explaining the implementation, what's going on different hardware units on the GPU, which we'll get into. But basically, it will move the data from the local P2P buffer to your actual like local workspace, and then it will then be able to start computing einsum A1B0 or einsum A0B1, which is like our second portion of the mapmul, and then dynamic slice update with that local result. And then now you see we have the full results here. Really quick, so this is a trace. It's not actually useful for like understanding the shapes involved, and like I found it a little bit easier to visualize just by actually drawing this diagram. So basically, this is the original all gather mapmul right here. And you can see we have two devices. A is partitioned row-wise, B is partitioned call-wise, and device 0 and device 1 here. And how it would work traditionally is we do an all gather, wait until the entire A is available on both devices, right? So you can see here we have the entire A on both devices. Then we do our mapmul, and then we have a shard of the output on each device, which normally would look like this, right? But they're partitioned, so it looks like this, okay? That's the traditional way. So what is this weird overlapping scheme? So here's our pre-allocated local output buffers, like we're going to be performing quote-unquote dynamic update slice on. So then first step of the operation, we begin the async send operations. We kick it off. A1 from device 1 will be sent to device 0, and device 0 will send A0 to device 1. Then while that's happening, we concurrently compute A0B0 to get C00, and then A1B1 to get C11. Here's the dynamic update slice. In real life, like in the code, I don't think this is a real thing, at least not in the PyTorch implementation, but it's just like an abstraction they are using to communicate it, I guess. Then here you can see finish async receives. So both devices, while this is going on, they can now move, that data is moving to their local P2P buffers. Then it can actually move from the local P2P buffer. I believe when they say finish async receive, they're saying move the data from the local P2P buffer to our actual region of HBM where we can actually manipulate data and use it for computation without interfering with comms and needing like weird cross-device synchronization. So we finish the async receive very fast. It's just a local copy, and then we can perform the next mapmul, right? You see A1 and A0 have swapped now, right? So now when we perform A1B0, we get C10, A0B1, we get C01, dynamic update slice, and now we have the full output on each device that we expected with the same exact data as we would have with our normal multi-device collectives, the traditional approach, right? We will retain the same semantics or equivalent. Okay, so that's how the all-gather mapmul works conceptually. Does that all make sense? Before we move on, I'll pause here just really quick in case anybody has any questions or comments. Okay, cool. With that, then we can look at reduce scatter or mapmul reduce scatter, which is a little more complicated. But let's just look. So basically, what this is saying is normally coming out of the tensor parallel region, right? If we look back at the original paper here, coming out of this, we already did an all gather, right? And then we go through this tensor parallel feed forward network, right? And basically, when we're coming out and we're preparing to do this last mapmul and reduce scatter, we already have the concatenated A's and the resulting activations that were created locally on the device as a result of concatenating those A's or all gathering those A's and doing the mapmuls, right? So going back to this paper, you can see this starts with the A's already all gathered. Like we've already and this isn't the same original A that came in at the beginning of this layer. We're now at a different layer, right? So A in this case is the output activations or intermediate activations, I guess you'd say, between these, going from the first linear through the gay loop to the second linear. Anyways, it starts with we already have both shards of this input activation, and we perform einsum, okay, mapmul with B0 to get C0, 0 and C1, 0. Same thing on the other device, and then finally we reduce scatter so that basically each device is only responsible for holding one shard of the reduced output. So you can think of C0 as being C00 plus C01, right, the left ones, and C1 as being C10 plus C11, the right ones, right? And again, these would be like a traditional nickel collective that is just like a blocking multi-device operation. Okay, so how is it decomposed? Basically, instead of shipping around operands, like we did with all gather, we're moving the operands around to different devices, the A tensor. Here we have a pre-allocated accumulator, like an output buffer, and we're going to move the accumulators back and forth, right? And yeah, so basically what it's saying is the algorithm works by always starting by sending your current accumulator to the next device, which in this case it's just two devices, so we send them back and forth to each other. They're just zeros, so it's like a no-op. We perform then we perform the local einsum, like the local mapmul of the partition that, in this case it's A1 in B0, which is going to be actually the chunk of the mapmul that's being reduced and stored on the other device. Okay, so this will produce C01, which you'll notice here, C10. If we look back at the top diagram, C10 is an index 1, and that's going to be responsible for being stored after reduced scatter on device 1, right? So we're computing that one first, not the one we're going to store locally, because then once we compute it, that local accumulator is going to be sent async to the other device. Then we do the next one, right? And so in the bottom one you can see here, this will be C11. So device 1 sent C10 down to device 2, it computes on device 2, or C11, and now adds it to that accumulator, and now we have C10 plus C11. Great, okay. So not super clear in this diagram. Personally, I just think it's like much clearer if we look at something like this. Here's the original mapmul reduced scatter. You can see all gathered. We already have the input activations are the result of we already all gathered the original incoming A tensor. So our intermediate activations here are like this shape, but our weights are still partitioned. So the computation would look like this, right? And we compute partial results. So A0, A1 mapmul with B0, BC00, and C10. You can visualize them like this if you break up the rectangles, right, into their corresponding little sections. And the reduction will occur along some dimension so that it kind of looks like this, basically. Like if this was not sharded like this, we would be reducing, say, like horizontally like this. C00 and C01 would be reduced into just one, say, C0 and stored there, whereas C10 and C11 would be reduced and stored here, right? But it's charted, so I diagrammed it like this basically. So, and I put this note here. This reduced scatter is like one nickel collective op in real life, but you know, for conceptually, you can think of it as like a reduce and then a scatter. So here you can see C00 and C01 becomes reduced, and same thing here. They end up having identical data, right? It's a reduction, so we have the identical reduced data on both devices. Same thing here. The pink is identical, and so I'll just call these C0 and C1. As you can see, they're identical. So the scatter part would be ensuring that each device is only responsible for holding some shard of that data, so we don't have duplicate instances of you know, C0 on each device, duplicate instances of C1 on each device, right? So our final result will look like this. Okay, so how do we achieve that with the overlapping approach? Here's our local accumulators, like I mentioned. So here's the thing: we start with A1 mapmol B. This is actually, you'll notice the output of this is actually going to be the C10, which is going to be part of the reduced result on device 1. So we're computing that first because we're going to move that local accumulator to the other device next, basically. And I mean, in this case, we only have two devices, so we compute the one we don't need first, ship it, then compute the one we need. Hopefully that makes sense. We compute the one we don't need first, we swap, and then compute the one we do need. So as you can see here, here's the part where we, you know, async send local accumulator. Right now it's just zeros, so nothing happens, while concurrently performing these mapmols, the ones we don't need to store on this local device, put them in that accumulator, right? While finishing async receive, which again, there's nothing there, 0. So it's just, you know, adding to empty and adding to 0, and we get C10 and C01. Okay, now here's the part where we start the next iteration of the loop, which is performing the same exact logic, async send of local accumulators back and forth. Okay, so now when this async send and receive is done, and we're concurrently computing the next mapmol, what it'll look like is this. You'll see the pink and the orange here have swapped. So hopefully that color makes it clear. They've swapped. So now we have C01, which is actually what we need to store on this device. No more moving around will be required, right? We wanted to reduce C01 with C00 originally. Remember, if we looked at here, C01 and C00. So now we just add our local result from this next mapmol to our local accumulator, and that's it. We have the final result. We don't need to do any, there's no separate step of like, okay, we have the full reduced output, and now we need to scatter it. And more importantly, I think probably the nickel collective does something smarter than what I diagrammed here on the left. But it's basically it's a non-blocking operation here to move the data between the devices for reasons that we'll see later, which they actually don't touch on in this paper, which is a little frustrating. So yeah, that's how mapmol reduce scatter. I'll pause briefly. Does anybody have any comments or questions about that one? Those are the two, we got through the two big ideas in this, and then we'll actually now discuss the technical details of how this is actually implemented in a way that works on modern GPUs.
Hey, I had a question in the chat. I'm not
Sure.
sure if you're reading.
Oh, no.
Oh, it's in the meeting chat. At this point, I
Oh,
put this. Yeah,
okay.
I was just saying that. I was just asking, like, this implies that the cost of reduce is actually more than the cost of doing this computation in a loop and like splitting the A into two parts, right?
Well,
Um,
it's kind of a complicated question. If you by cost you mean like the amount of data that needs to be moved over the network, it's the same. But in terms of, there's an advantage here we'll see in what the actual hardware used for this is, and that enables it to be overlapped. Basically, we'll see in a second the CUDA P2P comms operations that are done via like CUDA memcopy async. for contiguous data will be done by copy engines on the GPU, which are a completely physical, like a separate physical unit on the hardware than SMs. Whereas, which with like a traditional nickel kernels, that'll be SM-based comms kernels, which will create contention between your comms kernels and your communication kernels, or computation and communication kernels, which causes an overall slowdown. So I get the answer to your question, I guess, is yes, but for kind of complicated reasons.
Okay, yeah.
Yeah. Well, it'll become more clear in a second. I have a follow-up thing to show.
Mhm. Yeah, thanks.
Mm. Um, cool. So for this section, I'm actually not going to spend a lot of time on this really, or any at all. It's just, um, I mean, they try to, in my opinion, they basically try to be fancy and um, propose a generic algorithmic way of representing both of these all-gather matmals and matmul reduced scatters in one pseudocode kind of textbook algorithm style uh, notation here, sort of. It's like pseudocode, I guess. And they call it a loop collective einsum, which is like just a generic way of representing both. I think it's like less useful to go over because it actually, as far as I know, looking at the PyTorch implementation and reading about these actual implementations in the real world, this does not correspond to anything in the real world. Like, besides the term loop collective einsum, people use as like a style of computation and communication overlap. People will refer to it as like a loop collective einsum style overlap type of thing. So yeah, this we can kind of move past. It's just making pseudocode that generalizes both the algorithms we just talked about. Next, again, another thing we won't go over in a lot of detail. This is they basically propose a couple of scheduling algorithms to assign estimated latency to each of these operations, like the send and receives and the mammals and stuff, and then make decisions about basically do like a simulation, almost like saying, okay, at the current time, what ops have no dependencies in this graph? Like the dependencies have been completed, so there's no dependencies left, and their estimated latency has passed, right? And so it is quote unquote ready, and it is in the ready queue. And which other ones maybe are still in the pending queue due to either like dependencies not being done or latency still ongoing. So it like walks through this in this quote unquote bottom up approach and schedules them, prioritizing what they call collective done ops. So like collective permute start and collective permute done, or like async send start and like async receive done. And so it prioritizes collective permute done. My understanding is because basically that's where the dependency between the communication, it is the thing that will be blocking the next computational op from occurring, right? So the data is on like the local P2P buffer. Async, the collective permute done, I assume would do something like move it from the P2P buffer to like a local buffer. And then now we can do our local matmul with that shard that just arrived, right? So I think that's why they're prioritizing it. And this achieves like highest throughput, highest amount of overlap is the idea. Yeah, and then they discuss the implementation of the XLA compiler, doing the graph manipulation and replacement. They have a couple of optimizations like loop unrolling, which is like a traditional compiler optimization where we like break out a for loop of like 4 iterations and like 4 independent lines of code or like operations to get rid of some of the overhead associated with a loop. Bidirectional data transfer, I think they do something like basically, these shards sometimes are not big enough to where the computation takes sufficiently long time to overlap with communication. So they try to do bidirectional data transfer. I think what they're doing is like basically sending and receiving like multiple shards at once, so that they concatenate the operands of 2 partial line sums, execute them as a single operation. It's like a bigger gem basically, and more computation to overlap with. And it also helps fully saturate their ICI links. Yeah, the rest of this not super interesting, evaluating the results and stuff. So yeah, now we will move on to a little more detailed resource. As you notice, this is like super conceptual and generic and more focused on like algorithmic innovations, I guess. If we go here, this nice blog post from PyTorch goes over the actual nitty-gritty details, which I think is where the interesting stuff actually is. So here, what they call it in what's called in PyTorch is async tensor parallelism. So it's utilizing this quote-unquote loop collective einsum style overlapping to create this feature called async TP. And here they start by introducing tensor parallel. It shows the example, two-layer FFN sharded in a tensor parallel style with the all gather and the reduce scatter, right? Just like we talked about in this original paper. So, you can see we all gather our inputs and then do matmls on each device with the all gather inputs on our shard of the local weights. Have our intermediate output activation still sharded here. Do another matml with the row-wise partitioned weights for the second linear in the FFN. Now we have these partial results that need to be reduced and then scattered to minimize the memory consumption. So that's where the reduce scatter is. So as you can see, here's the pattern we're looking for, right? All gather matml and matml reduce scatter. Okay. So moving on, you can see as it introduces async tensor parallelism, we see the same diagram from our paper, right? It references, this is like, these concepts are introduced in these papers. Wang et al. Is the one we just read. And basically, it discusses specific performance challenges of actually implementing this with CUDA primitives and on modern hardware. So let's see what those are, because this is where it gets more interesting in my opinion. So basically, the paper kind of hand waves, right? Remember, it's just like async this, async that. Like it's just like, okay, conceptually cool. It could be cool if we could do it asynchronously, truly with like no, contention or any kind of slowdown or like, but on the literal physical hardware, like where is it executed? Like, is there contention? Like, can you truly do these things concurrently with just for free? Like, why are we doing anything blocking at all then? So this answers those questions. Basically, it says, while it's commonly believed that computation and communication are two resources that can be utilized independently, in reality their independence is nuanced and contention does occur. In an intranode setting, most common for TP, nickel send and receive kernels utilize SMs to move data across NVLink, reducing the number of SMs available for the overlapping matml kernels and slows them down. Interestingly, the observed slowdown can exceed the percentage of resources consumed by communication kernels. Since cuBLAS attempts to select kernels that execute in full waves, the SMs taken by the communication kernel can tip the balance, causing matml kernels to execute an extra wave. So I believe what they're referring to here, if I remember correctly, is a phenomenon called wave quantization inefficiency, or magnified wave quantization, where if your comms kernels are using SM-based comms, the SMs are actually doing the movement of data over NVLink, then that reduces the amount of SMs that are available for your actual matml. So it can't do full waves of like 132 SMs, right? For your matml, and you have to they'll be decomposed into like potentially at the end there'll be like a partial wave, because we were only using, there was some set of, for every single wave of the matml we did, there was some subset of SMs being utilized for comms. So at the end there's some extra partial wave that takes basically as long as a full wave, even if it's like two SMs or two blocks that you're computing, because due to parallelization. Like if you're parallelizing across like n number of blocks, any one block takes like roughly the same amount of time as any of the other ones. So it's really inefficient to just have this like partial wave at the end. And so that's one piece of nuance here about just like waving your hand and saying async. Like how async, it matters a lot. So the other thing is two-way synchronization. This one, I don't know. Okay, I think it matters a little less, but I think it says, so let's just read it. It says nickel send and receive kernels prefer two-sided synchronization, meaning that both sender and receiver are blocked until the operation is complete. This approach is not always optimal for data transfers with intra-op parallelism. Depending on the scenario, it may be preferable to perform single synchronization for multiple data transfers, or choose between pushing and pulling data from remote peers. So I think basically what it's saying is, these basically it could be more efficient to do a single synchronization, like a barrier, if there's like multiple data transfers, like multiple P2P comms kernels moving data around, it might be more efficient to do like one synchronization before, like one synchronization after for all of them, rather than having a bunch of two-sided synchronizations for every single send and receive op that happens. Like the traditional nickel send and receive kernels would be doing this two-sided synchronization for every single P2P op. And it's saying that there's like, more efficient ways to do this if you don't use those basically and do something else instead, which we're going to look at. So it says, fortunately, we can avoid these previously mentioned downsides by leveraging CUDA's P2P mechanism. The mechanism allows a device to access memory allocated on a peer device by mapping it into its virtual memory address space. This mechanism enables memory operations, load, store, atomic, etc., to be executed over NVLink. Moreover, when transferring contiguous data from or to peer devices via CUDA memcopy async, the operation is handled by copy engines and do not require any SMs, thereby avoiding the contention issues discussed earlier. So this is exactly what I was saying, where the implementation matters a lot and like makes or breaks this entire idea proposed in the paper. Whoops, I don't know what that is. And so essentially, to enable this, they developed this abstraction called symmetric memory, where essentially, there's going to be some P2P buffers on each device that are registered with like symmetric memory abstraction as like part of this tensor parallel group or this like process group. And each of these buffers will be mapped into each other's virtual address space. And when, say, device 0 tries to do a read from the virtual address space that is that a remote piece of memory is mapped to, right? Due to virtualization, it's like doing a local read, but the actual physical data is on a different device. But that read will then use multicasting to actually implement the data transfer, right? And that's how it works under the hood. And then they just say, and then it's very important, I should emphasize, the fact that when doing contiguous data transfers from peer devices via this CUDA API, CUDA memcopy async, it's handled by this completely separate hardware unit copy engine. So it's not using SMs-based communication like we discussed earlier. So you won't, in theory, run into these kind of like wave quantization magnification issues. Okay. Super important. So like the implementation details are critical here. So yeah, moving on. So now we get some nice diagrams showing how a naive implementation might actually be less efficient. So the quote-unquote naive implementation is how I pictured it in my head, and like makes the most sense to me. Which is basically, here's comparing with the original all-gather matmul. You can see A0. I'll zoom in a little bit. A0, A1, A2, A3, and then we have our B, whatever portion of the weight tensor we have here. And we see this big matmul occurring here. I'm unclear if this is supposed to, like if they're trying to communicate this also includes the all-gather, or if this is assuming the all-gather is already done. But either way, you can see, maybe there's like one partial wave at the end due to some like ambient computation, right? So maybe there's like 16 waves and then one partial wave to do this full matmul, right? If we do the naive implementation, like the most straightforward implementation of this micro-pipelined approach, we would do our async send and receive in one stream on copy engines, right? So send A0, receive A1, while we're doing the matmul on the first shard of A, like we discussed previously, right? And we're using CUDA streams to in our actual implementation to do this concurrently, right? And then we have a partial wave for that, say, because let's say this is like 4. So say for each of these, there's 4 shards of A, right? And say we said that was 16 full waves plus a partial wave at the end, this yellow. This might be 4 full waves plus a partial wave here, this yellow. And then synchronization. The synchronization is necessary to ensure we're about to do a bunch of cross-device data movement, right, from like everyone's P2P buffers. And we need to make sure that everybody's actually moved the data to that P2P buffer and it's like ready to be moved, right? So we have a barrier there, and then we start our next matmul and our next send and receive, right? But the key thing is that they're trying to highlight here is that each of these might have partial waves after them, and so you might have like 4 waves here, 4 waves here, 4 waves here, 4 waves here, but each has a partial wave, so you end up with the equivalent of 20 waves, because a partial wave, say, takes as much as just as long as a full wave. So, this would be 4 plus 1, then 4 plus 1, then 4 plus 1 plus 4 plus 1 is 20, whereas this was 17. I think that's what they're trying to communicate here. So this particular implementation is susceptible to this potential non-optimal scenario. This could happen. It's not like guaranteed to happen, but it's just like this is one way things could go wrong. So what they're saying is next they try to avoid, or not avoid, they try to minimize the effect of these partial waves by doing this alternating stream approach. So basically in stream 0, in stream 1, they'll alternate roles. So stream 0 starts by doing the matmul with the local shard that's already available on the device. The stream 1 will be in charge of doing the async send and receive. They call it post here. Not actually 100% clear on why they use the word post instead of send. Anyways, the point is that with the alternating approach, that means on stream 1, we can actually start. So the partial wave, remember, it's only utilizing a subset of the SMs. So if we're only doing computation in one stream, we just have to sit here and wait for that partial wave to finish before the next scheduled matmul can begin running waves, right? Here, though, if we switch to this other stream, it can start running the A1 after we've finished fetching A1. We can start running waves on the remaining SMs that are not being utilized in the partial wave of A0B, right? So you get some amount of overlap. So basically the negative effects, the wasted time of the partial wave is mitigated by overlapping it with another submatmul, basically. And that's the idea. And then they look at, that's the way they combat the magnified quantization inefficiency. So, and if you look at the streams here, basically, let's look at the baseline versus the regular. Actually, first, let's look at, so you can actually see in the trace some overlapping occurring here. You see the kudu mem copy async is always fully overlapped, right? Very cool. And then you see a little bit of the computation and computation overlap, right? Just a little bit. That would relate to like the partial wave overlap we were talking about. And then if you compare baseline vanilla TP with this async TP trace, you'll see, here's this all gather matmul, then matmul reduce scatter, right? Like for like a 2-layer FFN, you see the comms are completely exposed. There's no overlap. Versus here, all of the comms are overlapped from what I can see, right? And so, yeah, that's the idea, basically. And so what does this actually give us, at the end of the day? In end-to-end evaluations, you get something like an 8% E-to-E speed up on representative models like Llama 3AB, Llama 7DB. Forward pass turns out is accelerated much more than the backward pass. Not 100% sure why. Would need to look into that, but yeah. Anything else interesting in here? Oh, there's one other cool thing it does, which is it can detect, just like in the paper we talked about in the XLA compiler implementation. It's a compiler-driven approach where it will detect these patterns and automatically apply this optimization by like replacing the subgraph with this micro-pipelined approach. It also does this. What is this? But it can actually do multiple matmul. So instead of just all gather matmul, it can do, if one all gather is going to be used in 3 different matmuls, like say Q, K, and V projections on the input activations that are coming into multi-head attention, we need to do the projections, right? So it can do like this micro-pipelining approach to like a all gather, multi-matmul, basically. And yeah, the trade-offs here, as you might expect, needs to be sufficiently large problem size. This won't work very well with like very tiny matmuls. This extra overhead is not worth it because there's some amount of overhead, right, in this decomposition we're doing here. Like there's work required to do it. So you need to spend sufficient enough time in gems to where it becomes actually like fully overlappable and worth it, basically. So last, we'll look at one tiny portion. I guess I'll pause here first before the last thing. Does anybody have any comments or questions or thoughts on any of this?
Okay, I have a lot of questions. Sorry. Uh,
Sure.
uh, so first basic question is, I totally missed what these streams even mean. Like, so you're saying like NVLink, like physically, what do these streams mean? Because we only have like one set of SMs per GPU, right? So like,
Yeah.
what's happening with this? Yeah,
It's just a programming abstraction provided by CUDA, like called CUDA streams, that enable you to like
yeah.
concurrently schedule and run kernels basically on SMs. So
Oh,
yeah.
so streams are essentially uh okay. So you'll have a CUDA kernel, and then CUDA kernel will this fetch operation, and the P2P communication is also happening using the SMs, is it?
No, no. So the P2P communication is happening via copy engines, which is like a separate hardware unit, and the communication, like the A0 at B, that's happening on the happening on the SMs. The streams just mean like on the CPU side when you dispatch kernels, you queue them up, schedule them to run.
Mm-hmm.
You can assign them to like different streams basically, and it just enables like some level of concurrency on the GPU. So um, yeah, yeah. So
Okay.
so this can
Yeah.
this stream can be doing stuff like copy engine movement, CUDA memcopy async of sending A1, receiving, or sending A0, receiving A1, and then also it can, and that would be on copy engines, but then it will also
Mm-hmm.
do A1 at B, which will use SMs, but you're just they're just scheduled or queued into these different streams, but it's using the same GPU.
Okay. And we is there is there any limitation of how many streams you can have? Because uh, from what I know and from what it sounds like, the stream is just a software level abstraction which has very little to do with the actual warp queue and the actual, the warp selection, which will actually send the threads to be executed on
Hmm.
SMs. Like, it seems like we can have as many streams as we want, or what?
Yeah, I think there's some, you know, best practices. I believe you're correct. It's just like a software abstraction that enables this kind of like concurrent programming model. But yeah, like the actual like warp scheduler and everything is like independent. But I don't think you don't just like arbitrarily add more streams. Like it won't get you anything. It usually has some logical number of streams that would correspond to like specific roles in your program execution model, right? Like you might have like a cooperative schedule or what have you. Um, or in this case, like this naive implementation, maybe you want to implement something with the one's responsible for comms, one's responsible for computation. I
Uh,
don't think you would actually just, I don't know, there'd be no benefit and just more overhead by just adding more and more streams.
um, okay. Like, I'm going to ask more questions if it's asked. Like, I just wanted to like so on that topic, like when you say overhead, this overhead is based on some context switching between the streams, or is it like what's the overhead coming from?
I assume so. To be honest, I don't know the answer to that in as much detail as you're probably looking for. But I know there's definitely some overhead because, this CUDA stream is going to have, associated things that are queued up in it, and it's like a, separate software abstraction that's going to require memory and, like needs registers and everything to execute. So there's some amount of overhead. I think you can have a lot of streams. I've just never seen in practice like 1,000 streams or something like that. But yeah, sorry, I don't have more
Yeah,
details on like the specific
no,
overhead.
no. Yeah, that's more because I know like except at warp level, there's always context switching. So
Hmm.
there must be something like this here. Okay. And oh, I had one
Yeah.
more question that I'm forgetting a bit. Um, yeah, I'm just trying to understand like the paper was at XLA level, so they're literally alternating, like they're literally modifying what the compiler will do, and this is more at the PyTorch framework level. Okay.
Well, they're both.
So,
So the PyTorch, I can show you really quick. Like if you look at this, it's still in PyTorch, it's the same. So this is inductor postgrad passes, and you can see like views all gather mapmul. Like this is It's if we look at where this is used, this is the actual effects graph, right? And we're performing graph manipulation on it before anything is actually executed, right? So this isn't the only thing. Like if you look in postgrad, there's like a bunch of other optimizations and graph manipulations applied here. One of them, if you apply this async TP inductor config, then it will perform um, exactly what we talked about, fusing all gather matmals and fusing matmul reduce scatters. And yeah, I'm happy to go over the implementation of that, but there's a lot of code, so just for time's sake, I
Yeah.
wasn't planning on going into it. But yeah, it's the same thing. It's looking
Um,
at the graph and using pattern matching to find subgraphs of all gather matmuls or matmul reduced scatters, and then it's replacing them with these like fused implementations.
yeah, that's really cool because all of this is very reminiscent of flash attention. So it's really cool that they've like literally done it at the compiler level, and I'm guessing like I don't know like how much will this impact flash attention? Because flash attention also tries to do all these splitting of the A's and B's. Okay, that's really cool. Yeah, thanks.
Yeah, I'll just quickly go over. There is one section I wanted to go over the implementation just because I won't go through all the graph manipulation stuff, but just the specific little code snippet that corresponds exactly to what we were talking about today. This approach, like how the micro-pipelined symmetric memory-based alternating stream implementation works, you'll see it's actually pretty cool. So, full context, I don't like understand every single detail of this, but I'll show what I do know. So, this is called pipeline multi all gather and consume. Basically, if you look, like where this is used and stuff, like it's in it starts in this fused all gather matmul implementation. You follow the code far enough, you'll get to the pipeline multi all gather and consume. So that's just basically doing what we talked about, where it can do multi all gather and consume. Right? There's potentially we're doing like all gathers and like multiple matmuls basically. So we're just gonna look at the simplest case, where there's just one all gather and one matmul. Um, But if we look, I don't actually find this pseudocode like super helpful. It's easier just to look at this. You see, this group name, this process group name, will have already had a symmetric memory initialized, and so we look and get at the symmetric memory workspace, and our rank and world size and so on. Then we importantly do a barrier, because before we start reading and writing to P2P buffers, we need to make sure that everyone is actually at this point in the graph where we're again, like this is a very, you know, tightly, not coupled, what is the word? We need everybody to be working in unison at the same time in coordination for this to work. All the ranks need to be ready. All of them need to be executing these kernels in this finely orchestrated mechanism, right? So we need to make sure everybody is ready. Okay. Then we create this new stream, right? So we're gonna have our current stream and the second stream they call the backend stream. Okay. And this will synchronize with that stream. Make sure nothing starts executing on this stream until this one is all done with whatever was already running on it. Okay, cool. Now this is the cool part. So we've talked so much about async P2P SM comms versus copy engine comms. Like it sounds like you'd get some like super gnarly code, but actually in PyTorch it is like this very very simple code that is semantically it retains like single device semantics basically. So dest and source tensors, right? Um, S is our like a local like a tensor that's like in our local memory, just regular like HBM memory, and then D would be a remote P2P buffer. So some piece of memory on a different device, which has been mapped into our virtual address space, such that when PyTorch tries to move this data from HBM into this region of its into this region of what it thinks is HBM, is just virtual addressing. It actually under the hood is going to be moved with CUDA mem copy async via some C++ code, some CUDA, yeah, the CUDA code that does mem copy async, and it detects and knows that this is a region of memory that is on a remote device, and it will use multicasting to actually implement the data transfer. So sounds scary, but at the end of the day, since we have these nice Python bindings, we can just write this. Very simple, right? Just one little line of Python. Okay, get P2P buffs. All this does is just get the associated region of Rebus symmetric memory workspace, right? So symmetric memory workspace, there'll be some region of it, some region. So like if we have a device, if we have a process group with size 4, right, like 4 devices, then we'd have, the first quarter of it is, the P2P buffer, and we want to be able to send and receive stuff from device 0, next one device 1, and so on, right? So these are the regions of memory that are registered with and managed by the symmetric memory software, like APIs. Cool. So how does it start? We get our local P2P buffs for our rank, right? Then this is not actually important. This is just preparing if the user wants to return the all gathered output of the A tensor. It's like preparing this list basically, where these are actually A, like the shards I. This is empty. This was an initialized like empty output buffer for the all gathered data. So it's just putting them in this list for, I guess, the programming model is like easier when you can do like 2D indexing or something, I assume. Anyways, in this parallelization strategy, there's some nice detail here. So it has some diagrams. So if we say, it says after each rank copies its shard, local shard, into its local P2P buffer, every rank issues independent P2P copy and then shard consumer. Shard consumer is the matmul. Like you pass in the type of matmul you want to do, like the actual PyTorch op as like an argument, okay? And it will consume the shard and perform the matmul with it. So yeah, it does this in 2 streams, like we just talked about, alternating streams. So everybody moves data to the local P2P buffer, then there's a barrier, and then once everybody's ready, we issue independent P2P copies, shard consumer in 2 streams, and then this alternates the roles of these streams back and forth. So this talks about how it's, in addition to computation communication overlap, it also has computation and computation overlap, which I believe is referring to the partial wave overlap where we're reducing the quantization inefficiency. So MB is a copy to a local buffer. I believe they mean moving this to like a local P2P buffer, right? So to the symmetric memory buffer, right, from our actual like local buffer where we can use for like arbitrary computation. So MV is moving to local P2P buffers. CP is actually performing the copy, like this copy operation we looked at here. This is CP, right? And then B is the barrier. So there's different scenarios they outline here about when it can be optimal and less optimal, but depending on how things end up getting scheduled. But just look at the first simple example. Basically, stream 1, we have like shard consumer, which maps to, if we look at the diagram, like A0B here, right? And then MV would be moving data, our local shard, like A0, to that P2P buffer, then doing a barrier, make sure everybody's done with their moving of their local shard to a P2P buffer. Then the CP, everybody does a device-to-device copy, and then we start the shard consumer. And you can see there's a little bit of overlap here with the partial wave when it's only partially utilizing SMs. Then the remaining can get started on the next mammal. Okay, so that's kind of, you can see how the actual implementation is mapping to the concepts we talked about here. Finally, let's look at this is the rest of the code here. So you can see here, iteration 0, we start with moving our local shard, that's our source, to our local P2P buffs, right, so that other ranks can access it. Then we do our barrier, ensure everybody has finished moving their data to their local P2P buffer. Then we synchronize streams, right, and then we do our first matmul, like our A0B, right? And so this is we're dispatching the kernel for that, I guess you could say, on the current stream. And then for each iteration, we're going to do one iteration for each of the remaining members of the process group. We're going to alternate streams, right? So right now we're starting with step one, so this would, this would not be true, but so we would hit this else here, and we would switch streams. The current stream is now the backend stream, right? Then we check what remote rank we're going to be pulling data from, right, to get the next like A1 or A2 or whatever. And we just add the rank to add our current rank to the step number, and then wrap around the group size, get the P2P buff for that remote rank. So literally, like, what is our region of our virtual address space that is mapped to the P2P buffer for that rank, and then we do our copy, right? We just do our copy from that remote P2P buff to our local shards for that rank, right? This thing we created up here in this loop where we are copying each tensor, a subtensor, like one at a time, right? So now we have, after the end of this, using the symmetric memory API, we'll have shards of remote rank available. We can now do our shard consumer, right? So just do the mapmul with that new shard that has arrived, and we tell it, what rank this is for, who's like, which is it A1, is it A0, etc. So it knows where the output's going, basically. And then we go back in the loop, and then we go to 2, and then we'll switch streams again. Stream equals current stream, right? See how it switches back? And then we execute this again, and then we loop again, and then we'll go to backend stream. Then so we swap back and forth like this. And then this is just nothing. This is just if the all gather, if somebody wants to return it, this is for that. And then we synchronize streams, barrier, so everyone's done, and return. So that's how it maps to, how the implementation maps to this diagram here, which I always think is really important. I feel like it's almost useless, or not useless, but like you start talking about these like dense technical concepts. I think it's like really important to see like literally how is this implemented, because I feel like it's stickier in my memory that way, anyways. Like I retain it better. So I don't know. Hopefully that was useful for everybody. Yeah, I see there's other comments in the chat, but yeah. Any other comments or questions on this? That was all I had for today.
Um, in chat, we are talking about whether this will work only with NVLink or with PCI connection as well, because NVLink has this upper bound of 4 GPUs internode, right? So, do you think about that?
Are you
Do you know
saying,
if
sorry, are you
how?
asking, is this limited to intranode with NVLink?
Yeah, like in the discussions you've mentioned NVLink, but NVLink has maximum 4 GPUs, so that's why I'm asking, like, can we also use it for PCIe or not?
Well, doesn't NVLink also have, can you connect like NVLink domains with like NVSwitch or something? Because I believe this will work with the TP degree of 8 as well, like an H100, like a VM with 8 H100s.
Oh,
I
that
think.
will all be internode. This is all internode, so we also
It's all intranode. Yeah, this all only works for intranode right now. And yeah, I could be wrong. This is just to clarify. I'm not 100% certain. I know for sure you get good results with like if you have 8 GPUs, 8 H100s with FSDP degree of 2 and then TP degree of 4. That's how I believe the benchmarks in this post were taken. I have ran it though with TP degree of 8. If I remember correctly, actually, I think you might be right. I think the performance for TP degree of 8 was horrible. And that might explain why. Um, so yeah, I do know though, I will say this team is working on supporting internode. Um, so I think they're talking about something like NVShem, one of these kind of lower level NVIDIA libraries or abstractions to facilitate internode comms. I don't know the details there. I just know it's being like investigated. So that'll be pretty cool. Because yeah, right now this is limited to small, just intranode process group connected by NVLink only, and only for very large problem sizes. But still, very useful because that's a scenario that tends to apply for like large scale pre-training jobs and things of that nature.
Yeah, it's definitely much more than what I have done. So yeah,
Mhm.
it's much more efficient with that. Yeah, thanks. It's really cool.
Yeah, it says yeah, requires NVLink connection between device pairs through NV switch to achieve speed up. Okay. Yeah, I am curious. I'm gonna follow up and see if it works with only 4 or 8. When I tried the CP degree of 8, the performance was terrible. That could have been for a different reason than we discussed. But I don't know. I'll look into it just for my own curiosity.
Yep, thanks. It's still a lot of interesting stuff. Even with four, like you don't really need 8 GPUs in a lot of situations, especially serving and whatnot.
Hmm.
Yeah, this is really cool. Thanks.
Yep. Cool. Any other comments or questions? Anything else before we call it a day? Cool. Well, yeah, feel free. I'll send this blog post in the chat in case anybody wants to just try it out, try out the async TP feature in PyTorch. Um, it also works with, like the easiest way to use it probably if you want to test it out is in Torch Titan. It will just, like, there's just a nice, like, config. You can just, like, edit the, um, like, enable async, oops, tensor parallel. Like, you just enable this and it will work, basically. If you want to try it out, experiment with different TP group sizes, and also it's composable with dynamic float8 TensorWise quantization. So if you're doing float8 training, which a lot of people are doing now, it's composable with TensorWise scales. It's not yet. It is composable, I should say, with rowwise scales as well, which has like lower quantization error. It's kind of like a more granular scaling factor, so fewer elements underflow, right? But you won't get as much speed up as with TensorWise because only the map-mole reduced scatters currently fuse properly. The all-gather map-moles don't fuse properly for very complicated reasons that I won't get into, but some new development work needs to be done to make that possible. Basically, it's not like an easy fix. So, yeah, feel free to try both of those out. And yeah, that's it. I guess I'll go ahead and end the recording.